Hey guys, well, good afternoon. I have a short lesson for you, and this kind of finishes off a lesson that I started with cohort A today after the test. And it's all about all the different kinds of stars we've seen out there. Okay, so it won't take too long. It's not 2 lessons, it's only 1. So if you take a look at this, this is a comparison chart, okay, what you're seeing on your screen right now, okay? And it's by no means a list of like all of the different types of stars that we've seen, but like just to give you a size comparison, okay? So if you look at this, our sun, okay, is in the picture, but it is down here, and I'll use a color that you should be able to see. I'll use blue. Our sun is down, whoops, what am I meant to do? Doesn't think I have a pen. Our sun's down there. Okay, so that's where our sun is. Now, if you look at how small it is, okay, relatively speaking, it looks like a tiny little dot. Okay, well, yeah, that's what our sun is. Actually, believe it or not, an average-sized star. There are not very many in terms of percentage-wise. Most stars are around the same size as our sun. Okay, we'll talk about that later. However, okay, there are a few examples of stars that make our sun look like a little speck, okay? And that is something that we're going to look at today, okay? So take a look, okay, just for comparison purposes. Our sun, that little dot right there in the center of that circle that I drew, okay? Now, if you want to look at some other stars, starting up here with Mira A, Mira A is much, much bigger than our sun, okay? We call it a red giant, okay? And here we have an orange giant right there, okay? We probably still call them red, by the way. Betelgeuse, another orange giant, okay? We have a yellow giant here. So the largest yellow star, we call it hypergiant. It's getting quite big now. Okay, and there's something else sucking it in over here. We think, another large object could be a black hole, pulling it in over there, HR 5171, so it says at the top. YV Canis Majoris, until quite recently, YV Canis Majoris was the largest known star in volume, not in mass, but in volume, okay? So the largest known star in volume used to be YV Canis Majoris, but now we've UY Scuti. UY Scuti is the largest star that's ever been detected. Okay. Now, if UY Scuti were in the center of our solar system, it would actually be engulfing all the inner planets, okay, including, I think, Jupiter and Saturn. Okay, so even part of the outer solar system. That's how big that star is. Okay, it's absolutely enormous. But it's only about 20 solar masses, so it's not, it might be 100 million times bigger than our sun in size and volume, but it is not 100 million times its mass. It's maybe 20, 30 solar masses, something like that. Okay, so it's physically large, it takes up a lot of space, but there are more massive stars. Okay, in fact, the most massive star that we have ever detected, I think, is one of the ones that are down here on this little bottom section here. This R136A1 has hundreds of solar masses, okay, and it's about 35 times the diameter of our sun. Okay, so it's quite large, but not as large, not even close. Look how small it is, that little dot right there. It's about 35 times bigger than our sun in diameter, okay? But the thing that's special about R136A1 is it's the most massive star ever detected. So it's got a huge mass, okay? It's like 300 plus solar masses. It's extremely bright also, okay? But not necessarily, its volume is not that big. So remember, that little dot that I just circled right here, this guy, okay? That star is the most massive star, but not the biggest volume star, okay? These stars down here are quite massive, but again, the smallest guy down here is the biggest mass, I think. This one's a little bit bigger. If you're blue or you're violet, you're much hotter than yellow or red, okay? Or orange for that matter. Okay, so the color of the star denotes its surface temperature. Okay, so anyway, we've discovered a lot of different stars out there. Now, by the way, what about this? This quasi-star? So this object here, this guy, okay, the quasi-star, the big yellow one, we're not sure if stars like this actually exist. It's only a theoretical star, but it would be by far the biggest one, so we're looking to see if they exist. We think they would have a black hole as the core of the star. And we think in the early universe there would have been a lot of stars like this, but we're not 100% sure. So, like if you look at it, it's the largest known star here is UY Scuti. So it's the red, this red one here, the red hypergiant, okay? That would be the biggest star we've ever seen actually with a telescope. This one here, the quasi-star, we're not sure if they exist. If they do exist, they would be much, much larger even than our red hypergiants, our red supergiants. Okay, now I gave the class today a handout. I think cohort A, I gave this to you yesterday. So yeah, let's take a look. I have made a little comparison here. So the most massive star known, 315 solar masses, okay, and 32 times the diameter of our sun. So that is quite large, but not it's not really as big as the really big ones get in volume. 315 solar masses is a lot of mass though, okay. The largest star by volume is UY Scuti, like I said, and that's 755 times the diameter of our sun. Absolutely enormous, okay? Much, much bigger than the most massive star. So this guy is smaller but heavy, right? So, you know, it's a much more dense star, if you like, the R136A1. Oh, the hottest known star is this weird looking thing here. That's not actually the star itself though. What you're seeing is the coronal mass ejections coming from its atmosphere. Okay, so that, like the hot stars in the middle here, is a really wild star with like, it spins fast and stuff like that. It is the hottest known star by temperature, with a temperature of 210,000 degrees Kelvin, which is around 210,000 degrees Celsius, by the way. It's much heavier than our sun, 16.7 solar masses, okay? But it is smaller in size than our sun, and we think this one is close to supernova, okay? So we think it's going to explode soon, and that'll be quite a spectacular show. Anything greater than 10 solar masses, as I told both cohorts now, will explode in the form of a supernova when it dies, okay? All right, so, and supernova, quite spectacular. They can outshine the galaxy that they're in when they explode, like the whole galaxy of stars. Okay, now there's a chart here. I'm going to zoom out because I can't see the whole thing. So let's see if we can just fit the whole thing on the display. I'm using the smartboard to show you this lesson today. Okay, so here we have, this is called a, what is it called? Hertzsprung-Russel diagram. Gosh, afternoon is my sleepy time. So this is called a Hertzsprung, named after two scientists, Russell diagram. Now here's the deal. Let's say we gave you a task, like here's my task for you. I want you to take a catalog of all known stars, okay, all the stars that we've observed, and put them on a chart, okay, organize them onto a chart. And that's exactly what a Hertzsprung-Russel diagram does, okay? So let me sum it up for you. This is not like when you see all these dots on this page here, that's not all the stars we've ever seen, okay? It's a sample though, okay? So you could have a much bigger, like sort of computer diagram of this, and you can see all the stars we've ever seen. But you get the idea. So this is just a sampling of it, but it gives you the gist of it, which is what's important. All right. What I want you to notice is the scale on the bottom. So here, I'll go back to blue. Here at the bottom, the temperature scale. So that's temperatures in degrees Kelvin. You can think of it like degrees Celsius for now. It's just a shift of 273 degrees, but it's fine. Notice here it's hot. Actually, I'll go back to black. For this one, it's hot here. And then as you go down to the other side, it's cooler. But what we mean by cooler is 2500 degrees here, so that 2500 degrees is the cold temperature, okay, of that, on the cold side of the scale. That's still pretty hot, right? 2500 degrees Celsius, or Kelvin. Okay, 3000 degrees on the other side is extremely hot. So we start from hot and we get cooler as you go up. Now, on the vertical axis here, it's brightness. I'm gonna go back to black again. I'll write it like this. Brightness or luminosity, but they say absolute magnitude. All of those things mean the same thing. And remember that number, this would be dim down here. And then as you go up the scale like that, at the top would be your bright stars, okay? With a magnitude of -10 and so on. Okay, remember, the lower the number of absolute magnitude, the brighter it is, okay? And somewhere around 6.5, like around here, anything below 6.5, so if this is 6.5 right there, okay, this would be invisible to the naked eye. But of course, you're using telescopes. Anything below that line, you couldn't see with the naked eye in terms of absolute magnitude, okay? All right, so anyway, so it's temperature on one side versus absolute magnitude, and we mean surface temperature. This is the temperature of the photosphere. Remember how the corona of our sun is much hotter than the photosphere? Photosphere is around 6,000 degrees Kelvin, okay, whereas the corona is 1,000,000 degrees Celsius. So think of it like this. The photosphere is that surface that you see, the disk. That's what gives off most of the light, okay, of the sun, and it's the temperature of that that determines the color of the star. So our sun is kind of yellowish. Its temperature is 6,000 degrees Kelvin, so I'm going to circle 6,000 degrees Kelvin right there. Now if we were to just go up and find our sun, there it is, okay? So our sun has a magnitude, an absolute magnitude of around like 3 or 4, okay? So if I find over here, its brightness is around 4, okay? But its temperature, surface temperature, is just over 6,000, or just under, sorry, 6,000 degrees Kelvin. Okay. We call this zone in here, where you see a lot of stars, that's called the main sequence. Main sequence. Okay. And that's most stars that we see in the sky are part of the main sequence. Okay. In other words, they're kind of small on the small side, right? We don't get a lot of big stars in number. Okay, the big stars are more rare. So most stars are on the main sequence, which means they're kind of average sized stars. Okay. Color, let's talk about color for a moment. Red is cold color, okay, in this color scheme. Yellow is around the temperature of our sun, okay, so that's give the yellow color. After yellow, you get hotter than that, it gets to white, and so here, these are white stars here, okay? And then from white, even hotter than white, is blue. And so there's some blue giant stars here, and hypergiants too, or sometimes we call them supergiants, okay? But yeah, so there you go, okay? That's basically, okay, so it's like a catalog, right? Now if I were to ask you, where is the hottest stars, okay, on the chart, the hottest stars would be in this zone here, anything above that line, okay? So here's your really hot blue stars, this whole area here. They're all the same temperature. They're different sizes, but the same temperature. Now the brightest and hottest star is this guy at the top, right? That is the brightest and hottest star in this whole chart right now, okay? Now there's some of the names, I can't read them on the smartboard, but maybe you can read them on your computer at home. But yeah, that's it. Now, if you move across the top where the brightness is high, we see some giant stars and some supergiants. Okay, so here you can probably see YB Scooty or UY Scooty here at the top. Like that's over here, this big red thing here. That is a red hypergiant. Okay, and that is, like I said, one of the biggest stars we've ever seen. Okay, the red ones can get really big in volume, but they're usually not very heavy in mass. The blue ones tend to have more mass, to be honest with you, even though they're smaller in size. Okay, so now that's that chart. Now I did put a chart in your homework that looks like this. It's a Hertzsprung-Russel diagram. It looks very similar to the one you just saw, maybe a little simplified. Now if you follow the instructions, it just says label the bottom axis temperature. So here, we're going to put temperature here, right? And that's going to be usually it's in a unit called kelvins, okay? Not degrees Celsius. But here they're hot, here they're cooler. Okay, so the hottest ones are on the left. Okay, anyway, if you read the instructions, it says that. Now it says label luminosity. So this is your luminosity, which means brightness. Like this. And this is like, -10 down here. Okay, maybe around 0 here, and then, +10 up here. Sorry, I got it backwards. -10 up here. And this one is +10. The negatives are brighter. I keep forgetting. Okay. So, like, that's what they want you to do. Now they want you to color some of the stars in. It says color the 2 stars. Like, I'll first label the blue supergiants in the top left corner, and then color them blue. So that's the blue supergiants right there. Okay. So please go ahead and finish this diagram. Like I said, it's a way of organizing the star types that we've discovered so far. So we've discovered all these types of stars, the blue hypergiants, the yellow giants, the red giants and hypergiants, the main sequence stars, which are all around the same diameter, okay, but they vary in temperature, okay, across the main sequence. So here, this whole area here, right, if I circle it, those are the main sequence stars. Most stars are on the main sequence, okay, that we discover in outer space. These little guys down here, I forgot to mention those. These are dead stars, actually. We call them, they're in the white area, so it's white dwarf stars, okay. Here, there's some, some dwarf stars down there too, that are reddish in color. So, that's basically it. I'm going to ask you to follow those instructions, and that's it for today. Okay, all you got to do is so what message can I give to you to make sense of all this? Look, we've discovered many different kinds of stars, and this diagram is just a way of organizing it so that you can look at it at a glance and say, all right, here's the hottest and the brightest ones. Here's some big ones that aren't as hot. Okay, and it's just easy at a glance to understand where a star fits itself onto the chart. Okay? All right, so guys, have a good day, and we'll talk to you soon.